We left last time was dupe. I'll talk a little bit more about that. So we're doing processes. So what do we describe? Fork, that's how you create a process. Wait, waits for a child to die, gives you information about the death of said child. And exec, which is weird, right? Exec is how you load a program into memory and execute it. And the whole fact of you loading into memory and executes, it means you've lost your calling environment. Because you don't have a stack anymore. You have no memory. So it is kind of a weird thing. All right, and then with dupe, we were talking about these entities, and I'll reiterate the entities. So you've got a process. Your process has your memory, right, which has code globals, heap, stack, void, stuff splattered around in there. Then in the operating system, the rest of this is inside the operating system. For every process, the operating system will maintain a file table, which is indexed by the file descriptors that you get. And then each open file will have a file table which points to a file table entry data structure. And the key thing about that is the seek pointer is part of that file table entry. Then the file table entry will have a pointer to a vnode. The vnode, there's one of these per open file on disk. So if f1.txt is open, by 7 processes, there's one of these. That's kind of the operating system synchronization point for that file. And then on the disk itself will be an inode, which contains the metadata for the file and how you find the bytes. And we'll reiterate, we went over a program, I think it was FS1. There it is, okay? So I opened the same file for write twice, okay? Which means, so when I start the process, and here I have the picture in my little open office picture here. Okay. When you open the process, this is what it looks like, okay? Or after you make these open calls, this is what it looks like. So you'll have file descriptors 0, 1, and 2, standard in, standard out, standard error. Typically when you call it, standard out and standard error point in the same place. It's just the terminal for output. And then we open file descriptor 3, which is file1.txt, and then which opens it. If it didn't exist, creates it. If it did, truncated it. And then we open file 1 again with a different open call, and so that's going to get us file descriptor 4, which is now pointing to a different file table entry. And these have 2 different seek pointers. Okay. So when I write Jim to FD1, what's going to happen? It's going to write down here Jim and a new line. Let's make that a better color. Okay. Right. It'll write those 4 bytes to the file, and then this seek pointer is going to get updated to be 4. Right. JIM new line, no null character when you're writing these things. And then in the second write, when I write plank to file descriptor 2, you'll notice its seek pointer is 0, so it's going to overwrite Jim, and now my seek pointer is going to be set to 6 here, right? And then if I went back and wrote on file descriptor 1, it was right on top of that K, right? Because that's going to be where seek pointer 4 is. Okay, that's how disks look. Now the dupe system call. You give it a file descriptor, it's going to return to you a file descriptor. Much like open, it will return to you the lowest unused file descriptor. And when it does that, it's going to have those 2 file descriptors point to the same file table entry. So now you have 2 file descriptors that are doing the exact same thing. You can use them interchangeably, and they will be doing the exact same thing. So if we change this code here, okay, so that instead of saying open here, we say dupe FD1. Right. Now our picture is going to be different. Let's get rid of these bytes because they'll be gone. And we'll get rid of that. Right. The first open will create. Right. So after the first open, it'll look like that, because it'll create the file table entry for file1.txt. And then when I call dupe, dupe's going to return to me 4, and all that's going to be is another pointer to that same file table entry. And again, it makes them interchangeable. So now if I call write on 3, it's going to update the seek pointer, and then if I call write on 4, it's going to use the updated seek pointer. All right, so if I go to this code here where it says write FD1 and Jim, right, that'll write Jim and a new line. It'll update the seek pointer to 4. And then when I call write on FD2 of Plank, it's going to start with that seek pointer of 4, so now it'll do Plank and a new line, right, and the seek pointer will be 10. Okay. Not too exciting, but something that's good to know. It wouldn't be that important, except there are 2 times where this idea of duplicated files descriptors comes in extremely important. Okay? The first is when you call fork. Okay? When you call fork, I have a picture down here. I do. Okay. When you call fork, let's get rid of this text. In fact, here let's do the example. Okay, grep file 3. There it is. Okay, good. So here we've got a program where it opens F3 and then it calls fork. When you call fork, the new process will get its own file table, and all of the file table entries will be copied from the first file table. So that means the pointers to the file table entries will be copied. Okay? So in this code, when I'm at this point here, my system looks like this picture, which is small. Let's make it bigger. There we go. Okay? Again, file table entry, seek pointer, vnode, inode. And then when I call fork, the process address space is copied, but so is the file table. And so all those arrows look exactly the same. So what that means is that now the 2 processes are sharing the same file table entry, meaning they're sharing the same seek pointer, which means that if one of them writes to this file, that write will be basically reflected in the other process. Okay? So in this code here, what I do is I call fork, and then I call sprintf just because I want to avoid calling printf. So I called sprintf so you could see the return value of fork, and then I called write on it. Right? And so what's going to happen is, let's say the first one gets control, the parent gets control first, the return value is going to be 22107, and so it's going to go ahead and write, fork equals 22107. Right, and then the seek pointer will be updated for that. I have no idea what that's going to be. Let's just pretend it's 15. I have no idea how many characters that is, and I don't feel like counting them. Okay, and then when the child gets control, the child will write. Right, but the child will write fork equals 0, and then it'll do that write call. And since it's sharing the same file table entry because of dupe, right, this will write fork equals 0, and it'll update this seek pointer to 21 or whatever it would be. Okay, so that's important, and that's because basically it's like you're calling dupe when you call fork for every open file that you have in your process. Okay, so that's important part number 1. Important part number 2 with dupe is that there's another system call here. Oh, it's in there, called dupe2, very imaginatively named. What dupe2 does is you say, here's the file descriptor I want to dupe, and by the way, instead of you picking a number and giving it to me, I want it to be this number. And if this file descriptor is open, close it first and reopen it as this guy. And the reason we use this is how we redirect standard input and standard output. Okay. So let's take another piece of code, although, yeah. Is this the one I wanted? No. Oh, this one's fine. Okay, so what we're going to do in this example is we're going to open file 4, for writing. And then we're going to call dupe to, well, terminology I'll use is I'll say we're going to dupe it on the standard out. Right? We call dupe to, which is now going to close standard output, reopen it, so that it's coming from this file descriptor. So now it means anything that goes to standard out is actually now going to file 4.txt. Okay? I can close the original file. It's like a link. Once I've made this dupe call, these two are equal. There's no hierarchy that says I created FD and then called dupe, so FD wins over dupe. No, they're now equivalent. So when I close FD, that's gone. And now when I'm writing to file descriptor 1, it's going to go to file 4. So all of my standard IO stuff, which I have here, all right, so I print standard output's going to file 4. Even after we close, put char works, fwrite if anyone uses any of these. Okay? All of these will go, since standard out has been duped, all of them are going to go into file 4. So okay. So what happened? I made this printf call before I opened anything, so that went to standard out. Standard out. But after this dupe call, everything else went to file 4. So cat file 4.txt, right? And everything else is sitting there. Now, I'm hoping you're thinking while this is going on, well, is there any interplay between buffering and this? Because I know buffering is a problem with the standard IO library, and he's using the standard IO library, right? And the answer to that is, yeah, there are issues with that. For example, if I say bin dupe2 ex2, and I pipe that to junk.txt, okay, and I cat junk.txt, there's nothing there. Why? Because when standard out is going to the screen, printf gets flushed every line. When it's not going to the screen, okay, it doesn't get flushed unless the buffer's full. You call fflush, and the buffer's not full here. So what happened was that printf statement sent those bytes to a buffer, and that buffer never got written. And so then we called dupe2 and changed it, right? So now all this stuff's going to the buffer. We finally flush it, so everything in the buffer is going to file 4. So that initial print statement here is going to be in file 4. Right, there it is. Okay. That's all because of buffering. Now, if I said fflush here, okay, now what's going to happen? Well, that first statement is going to be in junk.txt because it'll have gotten flushed, and then the remaining statements are going to be in file 4. So cat. Right, and then cat file 4. Yeah, nothing too exciting. We just always have to think about buffering when you think about the standard IO library. Sorry. Okay. Now, when you write a shell, and this is, well, it makes sense, but it was always confusing to me in the beginning. When you call exec.ve, your address space gets overwritten, right, and it doesn't return. However, it's going to use the same open files that were opened. If you open files before that exec call, it's the same open files after the exec call. It doesn't change your open files. So this is how your shell works. Right? If I want to do, let's say I want to do, right? I want to do what the shell does with, here, let's say cat f1.txt to f2.txt. Okay? So this is important for your shell lab because you're going to have to write this exact functionality. Okay? So what is the shell going to do? It's going to call fork, okay? And the parent's going to call wait. We're done. Parent's done with everything. All the parent cares about is when does that child die? Because when the child dies, that cat's process is gone. The child, on the other hand, has to do a whole bunch of stuff. Child's going to have to open up f1.txt and do a dup2 onto standard input. It's going to open f2, do a dup2 onto standard output. Then it's going to do an exec VE call or an exec LP call or whatever your exec call you're going to do to turn that into cat, and now cat's running with the proper file descriptors in the proper place, and then when it's done, the parent will wake up and you're done. So let's go ahead and write that code, because I'm guessing you would all enjoy seeing that code written, especially when it's on video, but it's in the lecture notes anyway. Over here, direct S. Now let's just copy something so we can have all the include files. So here, let's copy circ fs1.c onto junk.c. Comments are for children. Okay, so what are we going to need? We're going to definitely need a file descriptor. We're going to need a status pointer. Okay, we can start off by calling fork. So if fork doesn't equal 0, I'm the parent. I'm going to call wait status. I don't even need to look at the return value. Why? I only got one kid. I know who it's going to be. Okay, so that's my parent. My parent's done. All right, here we do a comment. Parent. All right. Now the child's got to do a lot of things. So the first thing the child needs to do is redirect f1.txt to standard input. So child will say fd equals open. Do I have f control? I do. That's nice. f1.txt o read only. Done if fd is less than or equal to 0, less than 0. Then p-error f1.txt exit 1. Right? And we're cool, right? If this happens, we'll get that error message, the child will die, the parents will wake up from the wake call, and it's like nothing ever happened. Right? So even though the child failed, it's all good. Right? The parent will wake up when it's done. Okay. Otherwise, it'll call dup2 of fd on the file descriptor 0. Right? And then it'll close fd. And that's important. You want to close fd because when you make that exec call, you don't want file descriptor 3 open. In fact, you only want 0, 1, and 2 open. Now, 2 it'll just inherit from the parent, but 0 is going to get redirected and 1 is going to get redirected. And then everything 3 and above will be closed. All right, so now we'll redirect F2, standard output. It's going to be very similar. In fact, we could have just copy pasted it. F2.txt. O write only. Or O create, or O trunk. Sign of the beast. I will duplicate that. All right. You definitely want to do that check. And then you're going to do a dup2 of fd onto file descriptor 1, and then you're going to close fd. And now we're good. All right. Now we've got our file descriptors the way we want. Now we'll make the exec call. Yes, Rowan.
You're missing a quote in your open.
Thank you. Okay. All right, so now execute cat. So now we'll do exec, let's just do exec LP of cat, null. Right, exec LP takes, that's the program you want to execute, and then you give it the argv array, including the first argument. That's why I have cat there twice, is that one's the program, and since it says p, it's going to look it up in the path variable, so it'll find bin cat. If I didn't have that p, I need to find the cat program. That one's done. Now we've got the cardinal sin, right? So p error cat, here exec LP cat, and then exit 1, although frankly it wouldn't have mattered at that point. Okay. Oh, I guess I would have needed an else there. I'll just put an exit here. Exit 0. There we go. Now I don't need an else. Okay, and we're done. Yes, Will. It's gonna, so that value gets communicated to your parent via the return, by the wait call. Okay, so right here, when I say wait status, that 0 or 1 gets put into that status thing, which often, like, the shell ignores it, unless you, in your shell scripts, you can test it, right? In your shell script, I can, you know, in a shell script, a Bourne shell script, I can say, you know, if a dot out, you know, then, and if it went correct, if it returned 0, it'll actually do the if statement. Otherwise, the if statement will be false.
Why would you want to check that? Why?
Let's, for example, you're writing make, right? And make's got to compile 7 things into an executable. Well, if the first one, compilation, fails, you don't want to do the remaining 6. So make actually tests the exit value for just that reason. And if you exit it with a 1, make then stops compiling. Okay. There are times when you want to do it. I mean, my current, you know, I'm writing my current cluster based on Git code, which is killing me. But in that code, I need to test to see if my Git commands fail or if they succeed. And so I do just, Git does that too. If I do a Git pull and it fails, or a Git push and it fails, it returns 1. Merge conflicts are the bane of my existence. Anyone else have problems with merge conflicts? Just 1 or 2. Anyone else, is Git documentation the worst ever? I mean, I don't know if it is the worst ever. No, the socket man page, that's the worst ever. But at Git, they always, like, have you had this thing where you talk to someone knowledgeable in Git and their answer to you is always in like, you know, a language you don't understand? You'd be like, I'm having a merge conflict. And they're like, well, the upstream source of the fetch call when you rebased, the hell are you talking about? I don't want a merge conflict. Well, the local and the remote drives me nuts. Okay. All right. Well, we should see if this works, shouldn't we? Is it going to compile? Rowan helped us. No. Oh, God. Really? What's my problem? Yeah, what did I include? What did I forget? Standard lib. Yep. Standard lib has exit. Nope. There we go. All right. So now when I run this, what do I get? I should get an error. Oh no, F1 does exist. So it should work. What's in F1? Okay. So if I say dot out, now if I cat f2.text, it should equal f1.text. If I remove f1.text and I get all a dot out, then I got a problem. Okay. What's another problem? Let's chmod 0 f2.text. Touch f1.text. Now I should get a problem on f2.text. Yep. Couldn't open it because it existed and I couldn't delete it, or I couldn't open it and truncate it.
What if it was
A
a link?
link to
F1. What if F2 is
oh, crafty. Let's find out. I'm trying to think what's going to happen. I think it's just going to zero it all out. All right, well, let's put something in f1.text. I like how you're thinking. Here you go. Random names 10. God, so I'm writing my lecture note, or no, I'm writing up the lab write-up for the new shell, and I just want to create a file that had 10 names in it, so I use random names. First one had an offensive name in it that I couldn't put in the lab write-up because it would get me in trouble. I wanted to say what that one was. Second one, person had a last name of Hitler. How did that get, that's in the dictionary? So I had to get rid of that too, so that it had, so now we have fine names. This one has fine names too, it looks like. Okay, so now what do we, all right, so now let's chmod 0644 f2.text, remove chmod 644. Let's remove f2.text, and now we're going to link f1.text to f2.text. Okay. What's going to happen? Okay, so the first open command here is going to succeed, right? I'll get a file descriptor for it. The second open command is also going to succeed. The file exists, so it's going to truncate it to 0 bytes. Now, the Unix semantics here, I'm not sure if they actually are precise, but I believe what will happen is now, since it truncated that file, this one's not going to have any bytes in it. And so the read's now going to fail, no write, and now both F1, the files are going to have 0 bytes in them. That's my guess. Right? Do they have bytes in them? Now they do, 154 of them. So now if I call edit out, yep, now they have 0. Okay. As I said, it depends on the semantics of the operating system. There are some operating systems that say, whatever the state of the file was when you open it, you get that until you close it. And so the operating system has to do a lot of work on that to make sure that what happened with Unix didn't happen. But what happens with Unix is fast. And their argument is, well, if you do this, you get what you deserve. It's a standard Unix argument. Do the right stuff, it's fast. Do the wrong stuff, you get what you deserve.
If you don't truncate, would it double the names? Just repeat them? You expect they're still 0 now?
Or will it be an infinite loop? Right? Might be. I don't. My prediction, that's a fun question. My prediction is. Too good. My prediction is that it's just going to double the file. Because it depends on how cat's written. Where am I? I'm executing cat. Right? So now, this is a standard I/O thing. What is cat going to do? Cat's going to call, it's probably going to call fgetS. It might call fread, but it'll probably call fgetS. When it calls fgetS, the standard I/O library is going to read 8K into its buffer, right? And then, I don't know. Yeah, it's going to read 8K into its buffer, so then you're going to be reading out of that buffer. Now you're going to be writing over top of it, and then the real question is, if the write call doesn't flush, they're not flushing the write call, so the read call will actually die. So I think it's going to duplicate it. Whereas, this is fun. Let's try it. What was the question? What if it?
If you get rid of O-trunk?
If we get rid of O-trunk. All right, so first off here, we got to do random names. We'll put 20 in. No, let's just do 10. Into f1.text. Are they still linked together? Yes, they are. And now we're going to kill the O-trunk. Let's make it O-pen. Because with O-trunk, because remember, it doesn't seek to the end, so if I don't call O-trunk, it's just going to overwrite it with itself. That's not going to be a problem. Now, if I call O-append, that's where the fun happens. I think. Nice. Infinite loop. Filling up my disk. Stop. So it did flush. That's interesting. I didn't think it would flush. Do you not look at that and think, I mean, I guess disks don't have feelings.
S3 though.
What's that?
If that was AWS S3, like it would be money.
That's a thought. I always look at that and I think, that's just an offense to my disk drive. You know? Like if my disk drive had feelings, it would be angry at me for having had to go through all that work for that. That's why I think video is an offense to your CPU and your disk drive. That was fun. Thank you. All right. All right, done with dupe. Let's click. I hope we can do the clicker question. I didn't look at it yet. Let's kill the video.